Okay, so all this while we have been talking about different neural network architectures, and we ended up talking about the attention mechanism and transformers. We are going to go into detail on transformers today, but before that, I just want to do a quick recap of the attention mechanism. So if you recall, previously, we were talking about sequence models and the fact that in real life, you actually have a stream or sequence of data that comes in, and you use that to train the model. And after training the model, you ask the model to make predictions of what will be the next thing that come out from a stream based on what has come in so far, right? We could also predict, okay, based on what has come in so far to make classification, right, of what it is. So there are so many things you could do with that. And all of this led to sequence models were really good in, time-based data, right? But also because language data also came in a sequence, it was also used for language data. But we found that you know, sequence models, recurrent neural networks, LSTM, GRUs, and so on, were not very perfectly suited for language data because language data typically you could have very long um, sequence lengths, long sentences, long paragraphs, entire long books, and the typical traditional um, sequence models were struggling because of vanishing gradients, which was eventually solved with LSTM and then GRUs to increase speed. But I think the biggest challenge was two things. One was, yes, speed of training and speed of inference. But the second biggest problem was that issue of the context length, right? When you push in a sequence, yeah, you have an internal memory, which is represented by a vector, which is just a string, a list of numbers that represent that internal meaning, right? The internal meaning of that length of, sequences that come in, right? Whether it's words or whatever, right? But the constraint was that that vector that represents the internal meaning, that context vector, had a limited length, right? And so by the time you use in a sequence to sequence model to take that sequence, compress it into a context vector, you lose a lot of information. You lose a lot of information. So by the time you now use a decoder, the decoder is not going to do a very good job of, recreating output, to match that input, whether it is in another language for language translation or a summarized version of it and so on. So attention came in to solve that problem as a result of research from a lot of the machine learning experts and researchers. And what they figured out was that they could take the decoder and connect it directly to the encoder through an attention mechanism rather than um, using a context vector, right? So rather than using an encoder to, uh, or an RNN rather, which is an encoder anyway, right, to generate that context vector and then take the context vector and send it to the decoder. They figured out that, okay, we could put an attention mechanism and use that attention mechanism, which is basically a mapping of the same sequence, right, coming in from the encoder to the output sequence that the decoder, would use. So in that manner, it allowed the decoder to see every single input that comes in from the encoder, every single part of the sequence, right? But not only to see it, but to also work out how each of the elements, right, in the input sequence coming into encoder, how each of those elements affect what the decoder is generating, right? So that mapping, which came out in a kind of matrix, right, is what we call attention. But after some time, we even found that, okay, you can just do attention of the input sequence against itself. And you train a network on that, and then, it begins to learn. So that is what, attention was. And if we look at the attention mechanism, yeah, I think I've kind of summarized it. The older sequence models would take an input sentence, compress it into one vector, which is a context vector, and send it to the decoder, right? Remember that C, or that hidden state, that's just a context vector, right? But a lot of information is lost because of that compression. So think about a situation where you are taking a 200 word or a whole page, or a whole novel, and you compress it into a summary of 200 words. And then you now want to get the French translation of that novel, right? Not by looking at that 200-word summary. You definitely will lose a lot of information. And that's kind of that's the kind of thing. So attention came in to solve that problem by bypassing the whole context part, right? And then you have the decoder basically connecting back to each of the inputs in the encoder and trying to figure out if I am decoding the next word that should come, after, because what are the words, I will look at all the sequence, each of the elements of the sequence that comes from the input, and then the attention mapping or the attention mechanism allows me to see which of these matters most in what I should generate. And that's basically what the attention mechanism is. And you find that as you are training the model, it begins to learn these relationships, what we call an attention map. Okay, and later on there so the thing is, in that attention map, you have the query key and value. The query is the current decoder state, what it is, where it is now, right? And what it is trying to look for. Basically, it's a representation of what it is trying to predict next. Okay. Then the keys are all the encoder states, which is basically all of the previous elements in the encoder, in the sequence that comes into the encoder. So this is a way of saying that for the current things I have predicted so far, right? Let me look at all of the things that came in as the input to see which ones matter most to determine what I should predict, right? So that is query attending to the keys, right? And that's basically what is. Query is, what am I trying to predict next? What am I looking for? Keys is, what are all the things that came in, right, that can possibly affect the prediction. So the query allows you to select which parts of the keys matter to the next prediction. Then the values tell you how they matter. Like, so there's query allowing you to select from the keys which ones matter. When you have selected from the keys which one matter, you now have the weighting. The value is like the weights. Think of it like the weights. How much does each of these matter? Yes, I've now selected the ones that matter, but how much does it matter? The value gives you that, and basically the information or the representation of you know the ones that matter in the keys. And that's what the attention is. So we looked at the mathematical view of attention, looking at it in that manner of decoder, looking at what's coming in from the encoder. And the mathematical implementation was basically to know how many of the keys or which of the keys matter, you calculate similarity score. That similarity score is basically queries, which are series of numbers from 0 to 1, or sometimes in a wider range, times the keys, which are also a series of numbers from 0 to 1. And that gives you a score, which is basically how much each of the elements in the keys matter, as far as this particular query is concerned. And then from this score, you now get a probability distribution by softmaxing it, right? So that it sums up to 1. And then you typically scale it so it doesn't lead to exploding or vanishing gradients. And then when you take that, you now look at V, which is the value of each of those keys. And you essentially, the softmax is saying the ones that are not important, yeah, you mask out their values. The ones that are important, you bring out their values. And that's what attention is. So this was attention between decoder and encoder. But later on, yeah, so this is if the vectors grow large, the dot products can blow up. You can have vanishing gradients or exploding gradients. So how you fix it is by applying a scale factor, which is the square root of the depth of the uh, the attention vectors, basically, or the attention matrices, which you can say is the embedding. Well, it's not the embedding size, the depth of the embedding. Yes, that's what it is, the embedding. You have the sequence length, which is the 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 number of keys and the number of values and so on. So so eventually um researchers continued using using attention, to connect encoders to decoders until they figured out that, well, we probably don't even need to do that. We can just take a sequence and do an attention matrix of a sequence against itself, right? Rather than using the sequence that goes into the encoder against the sequence that comes out of the decoder, right? You can just take a sequence and do an attention against itself. And that resulted in what we now call self-attention, right? And so this led ultimately to a situation where we didn't need the sequence models anymore, right? You just take this the entire information, the sequence, and we just put it in directly, right? And that's what led to the transformer architecture, which we are going to talk about very soon. But the interesting thing is that the self-attention allows us to see how a word, affects another word in the sequence, right? After you have trained the model, that is, as you are training the model is learning the relationship between these words, which one matters most, to the meaning of the other word. And that was it. So this is an example of a self-attention matrix where you see that this is the sequence across and it's the same sequence down. So that the self-attention matrix allows you to see how each word, affects the the other word. So you could say, for example, for this word THED, this 0.40 is a measure of how animal affects the meaning of the. And of course, you can see this is very large because the really, when you're talking about the, you're always talking about what follows the, right? So that makes sense. And the rest of it, the meaning of the is not really affected by these other words, right? It's affected more by this word animal. And the same thing too, right? You can look at all of them. And it, you now see that it, animal also is the one that matters most to the meaning of it, right? There's also tired, but you can see its value is very low. So the one that has the highest value here of 0.46 is animal. So again, when that means that it's the meaning of it is really more affected by animal. And this is what attention matrix is, just a way of looking at it. Of course, it's not the actual words that we are doing when we are looking at attention matrix. Rather, it is the embeddings that represent these words, right? It is the embeddings. And remember, an embedding is basically a vector, a long list of floating point numbers or numbers, that represent the meaning of a word. So that is self-attention. So from self-attention, you can see it's the same kind of um, mathematical equations that we use. Basically, you start off by taking X, which is the original input coming in. You do what we call a projection, which a projection is basically how much the how you take this input and you you take a sub of it. I wouldn't say a subset, right? You project it into a another space, right? So it's meaning basically in that space, right? So and that's what we do. So we take the X, we project it across the weight of Q, which is a learned parameter, right? And that gives us a Q. So Q is a projection of X, onto a particular subspace. Um, K is a projection of X also onto another subspace. And V is also a projection of X onto a third subspace. And each of these subspaces, it is the weight that determines the exact, nature of that projection. So this WQ, WK, and WV are the learned matrices, okay, which you train. That's part of the model's parameters for an attention model. So with that, you have your Q, K, and V. You now do the same thing we talked about. You do a dot product of Q against K. So in this case, because you are taking the same input sequence, instead of taking the input sequence from one and input sequence from another, we are going to look at that in detail when we're talking about transformer architecture. But in self-attention, you are taking the same input and you are doing Q, K, and V projection. And then you are doing a dot matrix uh, product against itself. So effectively, what is happening is this, right? You take this input X, right? You pass it through a projection. You get a separate projection for Q. You take the same one, you pass it through this, right? You get another projection for K. And you take the same X again, and you pass it through this, and you get another projection. So essentially, these are three dense. Each of these is essentially, think of it as a dense layer, right? A linear layer, right? With these W's as the length weights that does that projection. A linear layer, that's what it is, right? Then you take these projections, you now take these two and you do a math move, which is a dot product. So you are going to do another dot product here, which we can call a math move. A math move is a matrix multiplication, right? So that gives us, of course, you have to transpose the T first of all, before you take it. Sorry, the K, you have to transpose the K first of all, before you put it in here. So this outcome is the QKT, right? And this outcome is going to be very high. So you divide it by a square root of dk, which is the scaling, right? And then when you have done that, you do a softmax as well. So you basically pass that through this, and then you get the V coming in. So at the end of the day, you will now compute an output, which is QK mat move, scale it by square of dk, softmax it, and then do another dot product against V, right? So when this happens, right, what happens essentially is that what comes out of this is going to have the same shape as X. Yes, it's going to have the same shape as X. Well, it depends on the Q itself anyway, but it's going to have a sequence length that matches X, right? And then it now, but you now have an embedding, the embeddings that come from this, which by the way, you also had embeddings here because X is a sequence. So let us think about it this way. You have a few words, like a few words, right? Now, this A becomes a vector, right, which forms an embedding. The few also forms a vector, which forms an embedding. And then the words also forms a vector, which forms an embedding. And then the subsequent words, you also have vectors that form embeddings. And this embedding will have an embedding size. So we can represent this with E, which means the embeddings, right? E, I, where I starts from, 0 to N or whatever, or 1 to N, right? So when you pass this through these projections, you are still going to have the embedding size. This is basically going to be an embedding. And the depth of it is determined by this weight, right? Or the size of it, because the weight is what will transform this, okay, into this. Typically, you would want to have weight to, let's say um let's say you have a sequence of anyway, we'll look at that in detail, but it basically is going to transform this into this. And then this will have the same dimension as well. The V will also have the same dimension. You still have embeddings. Then when you do the math mole of this, right, you are just going to have only the attention size, which you choose whatever the attention size will be, maybe for by 1024. Okay. And then this 1024 will now be the size of this matrix, which when you now multiply by V, V still has the embedding size. So V will be back to 128, for example, assuming the embedding size, that is this size is 128. Okay. Because if this is 128, then this is also going to be 128, right? While the size of this would be something like 1024. Okay. And this will also be 128. Where 128 is the size of the embedding array or vector, while 1024 rather, is this dimension, which is, so I'm actually talking about a two-dimensional thing, right? Where you have one dimension this way and you have one dimension this way. There's also a third dimension, which is the batch. But in this case, we're just assuming we are dealing with a single batch anyway. But yeah, so that's that. So you're going to end up with 128, 1024, 120, 1024. When you transpose this, it becomes 120, 1024 dot 1024, 128. So what you have here, I think I missed this, is actually not going to be it's going to be sequence by sequence. So we'll look at the numbers in detail later on. Okay, so this maths, so this maths gives us, at the end of the day, a value which tells us how each of them attends to the other. Yeah, so this is what I was trying to explain. Um, you start off with X that has batch and sequence length, right? And then it has an embedding depth as well. Then, but you can then do the scale dot product attention after getting QKV, but we'll see how we'll get the QKVs. Then the DK is the size of Q, which is the last dimension of Q, which is basically the depth. So this is in a multi-head attention situation. But if it is a normal self-attention, then there will be only one head, which we can also look at. Yeah, so this is how you implement the scale dot product attention. In most cases, you will not have to deal with all of this because these classes have all been handled internally. So then we talked about mask attention, which is used for the decoder because for the decoder, I don't want to see the future um, events. You don't want to the sequence contains future events, but you don't want the attention to see those because you don't want it to learn from what the decoder was coming from the decoder. Rather, you want it to learn from what is coming from the attention array. So effectively you mask out all future um parts of the sequence, right? And that's why you apply these zeros. And there are many ways this is done. So I'll show you how this is done. So that's the mask attention we're talking about. And this is one of the ways it's done. You use a touch.treeU. So a touch.treeU is basically a function that would take any matrix and you can specify a diagonal. In this case, diagonal equals to 1. And then you see, okay, anything above diagonal 1 we don't want to we want to mask it out. So tree will normally give you the upper triangle of a matrix. That's why it's called tree U. Tree for triangle, U for upper. So it gives you the upper triangle for the matrix. And the way you can view it is this. If you have a matrix like this that already contains the attention, remember attention is a matrix. So once you've calculated it, I can then decide that I want the upper part of it, right? which is this case. Okay, so when you specify the diagonal as 1, it means it starts 1 above the middle diagonal or the main diagonal. If you specify diagonal as 0, you normally 0 diagonal actually always translates to the what we call the major diagonal, right? This is 0. But when you say 1, it will start from the one above it. So that's what tree does. So tree is going to return back a matrix where everything above here is retained, but everything below here is set to 0. So now what happens is that you will now turn this into a mask. So remember, you're using touch.ones. So touch.ones means that everything up here, the 1 will be retained, but here the zeros um will be returned. They will be replaced with 0. Then you convert it to Boolean. So when you convert it to Boolean, that means everything down here will be false and everything up here will be true. So then you now use the mask fill, right? So you now use the mask fill. So what the mask fill does is that whatever value that you have in this course, you will fill this mask. Where this mask is 0, it will not fill. That's what the mask is. But wherever the mask is 1, it will fill it with this minus infinity. So remember, up here, the mask was 1. So when you fill it with minus infinity, that means everything in this upper side will now be minus infinity. While everything down here will be whatever was there before, which is this course. And then when you do a soft marks on it, remember when you do a soft marks, everything that was minus infinity will now become 0 because minus infinity is the lowest number. So everything there will become 0, while this one will be properly normalized following the soft marks. And that's how you are able to achieve a mask attention. Essentially, all these values down on this side will be normalized based on soft marks to positive probability distribution, while everything above here will be normalized to 0 based on soft marks. And then you now take those scores and multiply by the weight. So remember, it still follows that process that we said where attention is still going to be Q, right? V, so you still did this QK transpose, right? We still did the QK transpose, right? Which is what we have here, okay? And then we still divide the QK transpose by the square root of DK. So remember, this is division. DK raised to power 0.5 is the same thing as square root. Then we apply the mask, right? So this whole thing applies the mask. So we mask out this part of it, and then we do a soft mask, right? So we do a soft mask. This is still part of the masking. And then we do the soft marks here. So we do a soft marks. And that is what will give us the masked value. Okay. Then, and that's it. Then when we take this soft marks, we now multiply this soft marks thing against V. So that gives us a dot V. So this now gives us a mass attention. And that's how this works. So this is what is used inside the GPT models. And whenever you see a decoder, encoder, so we are going to talk about that. We can actually implement this manually, and I think I'll show you a little bit the code for it. But then this is the code. I don't think we need to go into the details. I'll leave this as an exercise for anyone who wants to continue to just go try this out on your own, because these are already implemented inside the transformers. Okay, so we talked about multi-head attention, which is basically instead of having a single implementation of attention where you have, again, you have the QK matmu scaling, which is divided by square root of DK, then the mask, which we just showed, which is optional, then the soft marks, then you get all of that. So that is soft marks of QK transpose divided by square root of DK. That's what comes out of here. You soft marks it and then you matmul it with V, right? This is a normal dot product attention for a single head. But we now take this whole thing and we do it multiple times in parallel, right? And that gives us the scale, the multi-head attention, which if you look at it here, this is actually how it's implemented. Basically, it just means that we take the entire attention thing and we split it into heads. Yeah. So the interesting thing is that all of this is implemented inside a single class. So we don't need to worry about all of the mathematics ourselves. We just pass in the parameters that we need and it implements it. We can specify the number of heads, embedding dimension, batch, and all of that. So in as much as I would love to have gone into the details of all of this, but because we don't have a lot of time, I will just leave that as an exercise for each of you to do a bit more research if you want to know more about the internals of attention. But the main thing is that just know that this multi-head attention class is going to implement a multi-head attention for you. You specify the number of heads, and then you have the embedding dimension. So the embedding dimension is basically the remember, I gave you a matrix before. I said that there are two matrices, right? You have this and you have. So the embedding dimension is the dimension of the embedding, which in this case is 5112. And then, but you can also have this dimension is a sequence length, right? That's the length. That's the sequence length. Um, but that's for single head. There's actually a third dimension, right? Which would have been the number of heads. So if you have multiple heads, then you have multiple, this is separate from the batch dimension. So you actually have four dimensions in a typical attention implementation. And you're going to see it here. These are the four dimensions, right? So you have sequence length and this depth, decay and heads. So the thing is what we have in the attention model, the embedding vector is what is split into smaller units, right? So again, let me see if I can, yeah, I did say I'll explain that. So let me show you how that works, right? What happens is um, in a single head attention, again, let's look at it. You start off with X, right? The X is the input, which is a sequence. And remember, this sequence is just a sequence of words. Let's just take it to be a sequence of words, a sequence of words, right? This is the input. Now, this input X, you'll find that by the time we now do an embedding, right? So each of these words now becomes a single embedding vector. So you have an embedding vector here, right? And um, you have an embedding vector there. You have another embedding vector for this. You have another embedding vector for this. Another embedding vector for this. So these are four embedding vectors. Let's assume each of these vectors is of length maybe 12 or let's say 16, right? I'm not going to, just for illustration purposes. Normally embedding vectors are much longer, maybe 128, 512, like you are seeing here, right? This 512 is the embedding dimension. That's the length of the embedding vector. But yeah, just for the sake of understanding, let's assume it is 16. So it means that you are going to end up, right, with this input X is going to have a depth of 16, right, which is the embedding dimension. And then it's going to have a sequence length, right? So the sequence length is going to have a sequence length, which in this case, let's assume that the sequence of words is 1, 2, 3, 4. Well, let's assume that we have designed this particular transformer to handle a maximum sequence of, let's say, you know, all the way to maybe a length of, let's say 1024. So it can handle up to 1024 words, right? So that would be the sequence length. In fact, let me even go to the extent of saying, okay, let's go back and make this 128 so that we say, okay, the vector embedding size is 128 and the sequence length is 124, right? The sequence length is 124. So that's 1024 actually, not 124. Yes, so this is what is coming in basically. X is this. It's essentially, and there's batch as well. So batch means this is just a single sequence that we are training with, right? This is just a single sequence. If we are training with a that has 1,000 words, 1,000,000 words, then you have a batch dimension as well, okay, which we are not really going to. Now, so this is X. Then this X, you pass it like was mentioned, you pass it as a projection, okay? So if you pass it as a projection, okay, true. You are going to have three projections, the Q, the K, and the V, right? So you have three projections. And um typically the weight vector that you use, you can either use the projections to increase this or reduce it or whatever, right? But let's assume that it's still the same just for ease of understanding. So you're still going to get 128, right? By 1024, right? So that's now the then when you now do your when you now do your QK transpose, right? So there's a third dimension. Um yeah, so you have 128 by 1024. So when you do a QK, this is QK transpose. What you are effectively going to have is um it should actually end up with a 1024, right? By 1024, which is effectively how how each of this sequence of words attends to the other sequence of words, right? Um, so that's if you wanted to do a multi-head attention, we would have divided this 1024 into multiple heads. But if we are just doing a single head attention, we are doing 128 by 1024 times 128 by 1024. So this is going to be transposed. So we're going to actually get 1024 by 1024, which is sequence against sequence, right? Um, so this is now the QK transpose, right? This is the QK transpose. Okay, so when you have the QK transpose, you can then divide by DK, square root of DK, and all of that. And then you now have 1024 by 1024. You will now, of course, that DK divided by DK square root is the scaling. Then you do the softmax, but at the end of the day, you still have the same shape, right? You can also do the masking, but at the end of the day, you now take this and you multiply by the V, which is 128, right? By 1024. Okay. So that will now give you, um, you are going to transpose this. So you are going to end up having, the, 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 so here's the thing. In order for me to clarify this, right, I need to clarify the order of the dimensions so that it will be, clear because a few people may be wondering how how is the order of the dimensions? Why is it looking funny like this, right? So I'm going to show you in a second. Okay, um, so let's start off by asking ourselves, um, let's see. Let me take this off first. Typically, the order of the dimensions, right? If we go to the previous, let's just go back a bit. Um, so I want to explain this. If you look at this, you will see there is an order here, right? And the order that we have here is batch first, then heads, then sequence length, then embedding dimension. Basically, decay is embedding dimension, right? So the embedding dimension is not is kind of placed last. So even though the way I wrote it may seem like embedding dimension is before the sequence length, it is actually last. So let me rewrite that correctly so that we can actually see. If we are writing it properly, you will see that um, let's go back to that place. You see that the actual way it should be written is batch. The actual way it should be written is batch. So the actual way it should be written is batch. Let me do that. So let's assume that let's start again. I think I lost my annotation. But you have a sequence, right, of words. And then let's say this sequence of words is of length 1024. Okay. This sequence of words now is what we will use. That's our input. Then each of these sequence of words has an embedding, and the embedding vector is maybe 100 and 28. You know, the length of the embedding vector is 128. So effectively, what you are going to have is think of it this way. You have a matrix, right? 1024, that's the sequence length, right? And then you have 128, right? This is the size of each vector. There's also a batch dimension, which we can call B, which basically refers to how many sequences that we are training on. Okay. So if you look at all of this, you are going to get a cube. Think of it like a cube. You are getting a cube. Okay. Now, so what is coming in as X has this shape. The shape of X is batch, which is the number of sequences, right? Then the sequence length, which is 1024. Okay. Then the embedding depth or embedding size, which is 128. Okay. That's actually a dimension. That's how it's written. So batch first, then so if I were to actually write this accordingly, the if I have to be correct, the way I normally think about it is I put the X first and I put the Y. So the batch is the foremost dimension. So that is let's say this one going this way, then you can say this is well, however you want to look at it. There are many ways to look at it, right? But I think it's just having the understanding of which one is the most significant dimension first. There's what we call most significant dimension, just like you have most significant bit and all of that, right? The most significant dimension is the dimension that changes first. Sorry, that changes last. While the least significant dimension is the dimension that changes first. So think of it like numbers. The most significant digit, the digit that its value always changes slowest or last, while the least significant digit whose value always changes first. Okay. So, so this is X, right? When you now pass it through a projection, what the projection tends to do is it will add more features. Basically, a projection, remember, a linear layer is basically feature engineering. So it can actually feature engineer this, and then it can increase the size of this dimension. Basically, introducing, that's the projection we are saying. It basically maps this 128 size embedding vector into a different subspace. So a different subspace typically means you maps it into either a larger or a smaller embedding size or feature size. It could be a subspace if we kind of basically project it to a smaller dimension, a smaller dimensional subspace. So we can maybe reduce it to maybe 32 or 64, right? But sometimes you may increase it. So at the end of the day, what happens is that you have the weight vector WQ or WK or the weight matrices or WV that do this projection. So these are parameters that the attention will learn. It needs to learn what these values are and how to map this. So it is through the weights, right? Whichever one it is, WK, WQ, right? WQ or WK or WV, that you now map this from the initial embedding, which you created, into a higher dimensional or lower dimensional embedding space. I think it's typically higher dimensional, right? So when you do this, this is now what you place into your attention matrix. You have three of these, right? X basically, and that's what I was trying to draw in the previous page. So I can show you here again. So you now have X, okay? You have X here. It passes through the three matrices, right? The three weights, WQ, and you're going to get Q from it, right? And then if you pass X through WK, then you're going to get K from it, right? And then if you pass X through WV, you're going to get V from it. So essentially QKV will have the same shape because WQ, WK, WV typically have the same shape. So for example, for this one, we are projecting from 128 to 512, then the weight would typically be 128 by 512, and so on. So the three of them will be 128 by 512. That will be the dimension, because that is what we will need to effectively map a 128 to 512. This is now QKV. So this is QKV. All three will have the same shape, right? So that's the first part of it, the projection part. Then after projecting, then the next part is you now do the attention. So in the attention bit of it, right, you take the K on this side and you take the Q. And because this is a matrix, you are essentially going to create a dot product, right? And when you do this dot product, okay, you're essentially doing the Q dot K transpose. And remember the Q is 120. Sorry, so let me write it properly because I didn't write it properly before. Is batch by 1024, which is the sequence length, by the embedding. So in this case, I had projected it to 512. That is Q, right? I now do a dot product against K. But the K, we do a transpose. When you do a transpose, Transpose typically means that you transpose the last two dimensions. So the K transpose will now be 5, 5, 12, right? Okay, okay. 5, 12, okay. And 5, 12, and 1024. Essentially, transpose means what was here, I move it here, and what was here, I move it here. When you talk of in terms of dimensions, you are flipping it. Basically, you are flipping one of the planes. You know, you are rotating one. What is it rotating? You are flipping one of the planes. So that's what transpose is. So with this now, let's leave this batch dimension out of this equation for now, right? That's why I don't like to think about it, but just keep it at the back of your mind. You can now do a dot product between this and this, right? And this dot product, this middle dimension is the same, okay? So because this middle dimension is the same, when you do the dot product, it goes away. So you now have 1024, right, by 1024, and the batch dimension is still there as well. So this is now the shape of your attention matrix. In other words, think of it of this way, 1024. Remember, this is a sequence length, which is the number of words, right? The maximum number of words. So it's basically 1024 is 1024, and this is 1024, okay? So this attention matrix will now, if you were to plot it as, um, you know, a heat map kind of. This will tell you some hot spots, some not so hot spots, and so on. Basically, it's just telling you that in this one, this particular um, element in the sequence, right, attends to this one more, and things like that. So that's basically what this is. What we saw in the beginning, right? So we now get 1024 by 1024. We do transformations on this, right? The transformations we do on this 1024, 1024. Of course, the first one is to scale it. So what do we mean by scale? We divide it by square root of dk, right? That is scale. Then after the scaling, what's the next thing that we do? We do masking, okay? And then um, after masking, we do soft marks. So we end up with soft marks, right, of the QK transpose over the scaled value, right? That is what we now take. That's still going to have the same shape. We now take it and we do a dot product with V. So let's move to that step where we do a dot product with V, okay? So if we do a dot product with V, remember our QK scale QK matrix still has a 1024 by 1024 dimension, okay? Or comma, whichever one, it doesn't matter. It's just how we look at it. Now you take this and you do a dot product with V still has the same dimension as the others had before, which is 1024, right? By this embedding size or embedding depth. So when you do this dot product, again, you will ignore this batch dimension. You do the dot product between these last two dimensions. You always do dot product between the last two dimensions. Every other dimension ahead of it, you ignore. So if you do this, you now have B by 1024, because this one and this one will merge basically when you are doing that dot product multiplication, and you'll be left with one with this. So this is the shape of the result that comes out of your attention map. Now, this is for a single self-attention. Now, so when we are doing multi-head attention, what is happening is that instead of, I still have my QKV. Let's start again with multi-head attention. You still have your QKV, right? So let's back up. We're now doing something else. So the Q again is still batch, right? Which you can ignore, by sequence length, which is 1024, by the embedding depth, which 512, right? K is the same thing, V is the same thing, right? The only thing with multi-head attention now is instead of directly going to do the attention multiplication, we will separate this last dimension into multiple, let's call it channels. The same way we had filters, right, in CNN. We now take this and we separate it. So that is where the multi-head, we split it into heads, right? So each head, we can now say, let's say, assume I want to have 8 heads, like in this case where we say we want to have 8 heads. I want to have 8 heads. So if I want to have 8 heads, that means I'll divide 512 by 8. So I'm going to have 8 heads. The head, by the way, there's a transposition that is done. So the heads become the second dimension. So this will now be 8. The third dimension is still going to be the sequence length. We never change the sequence length. And then the fourth dimension is going to be the depth of each head, which is basically 512 divided by 8. Okay. So if we do that, that will be about 64, right? If I am not mistaken. So this will be 64, right? So that means you now have 8 heads, each of depth 64. Instead of one head of depth 512, you now have 8 heads of depth 64. So each of these heads now, because we are using the beauty of using multi-head is they can now learn a different ways of attending. And that's where the benefit of multi-head and expanding the dimension is that let's assume I started with embeddings of whatever, maybe 128. I can now have more features. I can have more heads. Each head comes up with a different way that they attend to each other. So our queue is still going to be B batch size 8, 1024, 64, and our K is going to have the same dimension. So when we now do our Q and K transpose, we're now going to have B batch size. We'll still have 8 heads. Remember, when we're doing math mole, it's only the last 2 dimensions that we multiply. So the last 2 dimensions of K will also be 1024 by 64, but we have transposed it. So for K, it will still be batch 8, but it will now be 64, right? And 128. Sorry, 1024. Sorry, 1024. Okay, so when we do the necessary, the 64s will cancel. And we're still going to get B8 1024 by 1024. So we're still going to get a matrix of the same size as a single head attention, right? But in this case, this particular, we'll have 8 of them, and each of the 8 of them is going to be a different kind of um, relationship, right? So that's where this comes in, because now you see I did the linear projection. The linear projection is basically X, times WQ or WK or WV. That's the linear projection that will lead you to having the Q, right? Then we split into heads. That's what I just did now, where we now take the original embedding dimension, we divide it into 8 heads. So each head is going to have 64, a depth of 64. In other words, an embedding dimension of 64 per head, right? And then each of these per head will still do the same dot product of QK transpose. And that's going to give us 8 attention maps rather than a single attention map. The beauty of this or benefit of this is that each of the attention maps will show a different kind of characteristic relationship between the elements in the sequence. So again, remember one single one single attention matrix or attention map was mapping, you know, each of the sequences, right? Remember, it's still the same sequences, 1024. So each of these sequences, how they attend to each other. But now each head can mean something different, right? One can mean semantic, how these interact or how they are related semantically. The other could mean how they are related based on sentiment or based on position or based on language or based on grammatical, they are different, each of the heads. So now we will have 8 heads. So we have a second head here. I didn't draw this very well, but I don't have a lot of time. And this tool is not really good for drawing. But think about this. You now have 8 attention maps. Basically, that's what 8 heads means. And, you have 1, 2, 3, 4, 5, 6, all the way to 8. So we have 8 of them stacked up. That's basically what this is. And this is H, right? H is the number of heads, which in this case is 8. okay, right? And then each head has a depth of 64. But of course, in the attention map, the depth disappears because the attention map does not really look at the size of the embedding, but the relationships, you know. So now this gives us QK, right? It now has this shape. So this B810241024, um that's a dimension or the size of the entire stack of 8 attention maps. Now, we take these 8 attention maps, we still go through the same process of, scaling it, which remember, scale is what? Divided by, square root of dk. And now dk is going to be the depth of each. Before dk was when we were doing a single head, dk is going to be 120 or 512, right? When we're doing a single head, dk is going to be 512 because dk is the dimension of the is this last dimension, right? Which is the size of the embedding or the depth of the embedding. But when we do multi-head, dk is now the depth of each head. So in this case, when you're doing multi-head attention, dk will now be 64. It's not going to be 512 because we are now each head has a depth of 64, which we had first of all eliminated with dot product, but it's still there, right? So we do the scale. After we do the scale, if it is a decoder, we'll still do the masking, okay, as usual, which I had already shown. After the masking, then we do what? The soft max. After we do the soft max, we now have a probability distribution. We can then take that probability distribution and do what? We now multiply that attention value. We multiply it against V, which is a value. So remember, V is this third one, the third projection. And the third projection has what? We don't do oh yeah, I forgot. There is what we call concat. So we will do concat. Um, yeah, we will do a dot v before the concat. We'll do concat after, right? So for us to do the a dot v, we still need to split the v again the same way we split the q and k. So we'll still split the v into 8 heads as well. So the V will also have the shape of B81024, which is the sequence length, right? And 64, which is the depth of each head. So we'll take this B81024 64 and we'll multiply it by the B81024 which is the attention. That's the shape of the attention, 1024. Okay. So when you do this, of course, remember, you always ignore when you're doing MATMUL. MATMUL is a two-dimensional operation, right? A matrix multiplication, you can only do it on 2 dimensions. So we typically do it on the last 2 dimensions. We ignore every other dimension before will just be maintained. So when you do it on this last 2 dimension, of course, this is the middle dimensions, right? This 1024 and this 1024. So you are going to end up with a B81024 and 64. So this is now a V that is still multi-head. Then we'll now do what we call concat. Concat is where you now combine it back, right? That is step 4. So the parallel attention is what we just did when we split into heads. So you are doing this parallel attention is where you are doing the whole, after you have split into heads, right? You now do the whole QK, transpose divided by square root of DK, right? Where DK is the depth of each head, which is going to be less at the entire embedding. You softmax it, and then you multiply by the V. So you're still going to end up with a multi-head implementation. Then you do the concat. So the concat is you have a batch, 8 heads, right? 1024 sequence length, and then each head is 64 depth. We'll now recombine these heads. That's the concat, and you end up with B 1024, and you are going to go back to 5112. because when you add 64 8 times, you are basically concatenating this 64. So think about it this way. You now have this thing where this is 1024, right? And this is what 64, right? So this is a flat piece, a single a single outcome of attention times V, right? This is attention times V. I forget about the batch dimension for now. And then we have 8 of them, depth of 8. In other words, we have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 of these stacked up. They were performing it in parallel. That's why we say parallel attention. This attention is done in parallel, right? But after we have finished doing it in parallel, what do we do? We take this parallel and we stack it back up. So we take this first one, right? And we put it up here. We take the second one and we put it below it, right? We take the third one. That's why it's called concat. We concatenate it, right? So we concatenate this all the way to the eighth one. And since each of them is of dimension 64, 64, right? 64, 64, 64. When we have concatenated all 8 of the 64, we're going to get back our 5112. And that is the dimension that we have here. So this is what multi-head means. It basically means take the embedding dimension, split it into n heads, do attention on each head separately, basically each attention, do it in parallel like this. When you are done with it, you take the parallel thing, spread it back out and stack them up, right? That's a concatenate. And then you do the final projection, right? So that is an explanation of multi-head attention. I really needed to explain that so that we can understand all of that. Okay, so with that, we have multi-head attention, and that's really what it is. And why I spend time to explain this is because this is like one of the most important layers in deep learning. I'm not going to do any more explanation. I think this should be enough. Now let's talk about transformers. So we said that attention could be used with recurrent neural networks, right? But the transformer was a new architecture that the Google team in 2017, they made a paper, right? And in that paper, they came up with a new architecture where they said, hey, okay, we are used to always putting this attention map, as a way to connect, the encoder to the decoder so that decoder can learn, about encoder, attend to each of the elements in the sequence that comes from the encoder. But they just came and said, hey, we don't even need encoder. We don't need decoder. We don't need recurrent neural networks. We can just use basic, what we call feed-forward networks, which is, dense layers, right? The attention is enough, right? This self-attention that we just did, where the sequence attends to itself, right? And knows, each word, how it is influenced by the next word. And then we now even apply this multi-head thing, right? That we just explained. That's all we need. And that's why they call their paper, attention is all you need. We don't need recurrent neural networks anymore. So they removed recurrence, they removed convolution, and it was revolutionary. Why? Because when you are training recurrent neural networks, you are training sequentially. You cannot paralyze the training. In other words, I cannot train multiple inputs at once. So think about it this way. I have a sequence of 1,000 words that I want to train on. So I have a sequence. We just did that. And we have a sequence length of 1024. Okay. For me to train a single batch of this, I have to take my neural network. I have to pass one token at a time. So token 1, I pass it, right? Token 2, I pass it. So for each time I want to train this, I have to do 1024 iterations, right? They are very fast iterations, granted, but it's still 1024 iterations. And training on that, then when you want to do back propagation, you still do 1024 iterations. It's crazy, right? That's why I'm going to show you an example where we are using BERT to train an LSTM to predict the next word, and it took a long time. But with transformer, Transformer, this 1024 items in the sequence, I put them into a single, you know, layer, into a single linear layer. And then I use attention mechanism, to basically attend to itself. So you have the projection. Remember, we say we have a projection. This is the QKV projection, right? Each of these will come up with something. The weights will now give you the Q, the K, and the V. But what is coming here is a sequence length of all 1024. And the Q is going to have 1024 as well. And the K is going to have 1024. So you can do a matrix multiplication of 1024 by 1024 all at once. It is a single operation, a single calculation, which you are even going to parallelize with a GPU. So it's a single calculation. So you can see that already this is a 1024 times faster than if I was using a sequence model. And that is the main power of transformers. The fact that RNNs cannot parallelize, transformers will parallelize. And because you can parallelize, you put them on a GPU. GPUs are designed to run parallel operations at scale, right? Parallel calculations. And then the long dependencies is, of course, because of the whole, attention matrix itself, the self-attention matrix, it's able to do that. And so that was what started the whole transformer um, revolution. Because this solved the problem. The biggest problem I think that the transformer solved was just the logistical problem, the pragmatic problem of how can we be training things faster? So that's transformers. Let's look at the transformer architecture, right? So, like I said, they removed RNNs. So you will not see anything like LSTM or anything here. What you are going to see is you still see the input, you still see the encoder, and you still see the decoder, right? So, let's start with this. If you look at this, right, this is the input. We have the encoder. So in a transformer architecture, we also have encoder and decoder, just like we have in a sequence-to-sequence model. The only difference that, of course, a sequence-to-sequence model, that's why it has encoder, decoder, right? For a standard, previous recurrent neural network, you would have an LSTM as the encoder, right? And then the output, the sequence output from that LSTM becomes the input to the decoder. And then you now have a dense layer coming out from the decoder. But in a transformer, this is the encoder, right? This is the encoder. And let me do this properly. The encoder is basically half of the architecture, right? So this is the encoder, and this is the decoder. We're going to look at each of these separately. But the most important thing that you see here is that they both have basically the same architecture, right? And these are the elements of them. First of all, let's talk about what each does. The encoder's job is to understand the context and to build the semantic representation. While the decoder's responsibility is to generate the output sequence, right? And to attend to the encoder's input. So the decoder needs to be checking the encoder input as it is generating the output sequence, okay? So that the sequence it generates is relevant, And then, of course, the decoder has to do this masking, right? It has to do this masking to prevent learning future stuff. It's not supposed to learn, it's supposed to predict. It's supposed to learn from the encoder and then predict, not to learn from itself. Okay. So in summary, you can see it as encoder does comprehension while decoder does generation. Okay, so let's talk about the specifics. If you look at this, you will see that yes, it has inputs, then it has the input embedding. So this input embedding is basically the same thing as creating an embedding vector. So an input embedding is where you change words, right, into the equivalent. So you can change words like, yeah, you have a sequence of words, hello, for example. You now take this sequence of words and you change it into a vector, right, of numbers, 0.5. 0.1, 0.3, 0.6, and all of that, whatever the length of that vector is. That is embedding. So that's the first step. Then we'll talk about position encoding. Position encoding is the second thing, and it is very, very critical. The main reason why position encoding is critical in the transformer architecture is because transformer is not inherently sequential anymore, right? It's taking all that information in parallel. So if it's taking it in parallel, how does it know which one is supposed to come first and which one comes last? In a standard recurrent neural network, right, the sequence of tokens is inherent, right, because it's sequential. But a transformer is just a dense layer, right? It's basically a dense layer. We are back to the original, architecture of using a dense layer, right? So it doesn't know which one should be first and which one should be last. So we solve that problem using positional encoding. We'll talk about that shortly. And then after position encoding, we now come in here. So you now see that we have the multi-head attention, which I just spent a bit of time explaining, right? It's basically attention. This is the projection. That's why you have three splits here. This projection gives you Q, K, and V, right? And this Q, K, and V goes into this entire multi-head attention block, right? And then you have what we call add and norm. So what's add and norm? Norm means batch normalization. We've not really talked about normalization. We've talked about standardization and normalization. There's something called batch normalization, batch norm, even though in attention, it's not batch norm that we use. We use layer norm, right? Layer norm means basically normalize. So let's forget about batch normalization. Layer norm basically means normalize the inputs or the outputs from each layer, right? That's layer norm. Normalize the outputs from each layer, right? That's layer norm. So when you have done the multi-head attention, the output from the multi-head attention, you normalize it, then you add it to the input, the original X input before it was projected, right? So the essence of this, remember, this thing is what we call a skip connection. And the purpose of the skip connection is to ensure that we minimize what do you call it, vanishing gradient. If you remember when we talked about LSTM, that's one of the things that they introduced to solve the problem, right? A skip connection kind of um, think of it like refreshes, this output by bringing a larger amount of the original input back to mix it in. So think of it like you dilute or you mix the output with some measure of the original input so that you don't totally lose the original input. That's what a skip connection is. So you see you have a skip connection here. And then this output is now passed through a feed-forward network. We'll talk about feed-forward network also shortly. And we also pass the output from the feed-forward network through, again, the layer norm, and then we add it back to another skip connection. So we have a second skip connection here, right? These two stacks of multi-head attention, add and norm with a skip connection. That's what add and norm is. The add is a skip connection. That on top of a feed-forward layer, that is what is the encoder. And then we take this encoder and we take the output from this encoder. So remember, the output from this encoder is just another output, right? We will still bring this encoder output, right? Okay, we are taking notes, we take the encoder output. We will now do another projection here. So we'll talk about this detail here. Then for the decoder, you see the same thing, right? You now see that for the decoder, you take an output, right, which is shifted right. This output is the data you want to train the decoder on for it to generate. So you shift it right, right? The reason why I have to shift it right is because it is, of course, you are trying to predict the next word, so you have to shift it right. You are still going to do an output embedding, which is the same thing like we said, just converting the words into embedding vectors. Then you're still going to do positional encoding as well, right? Then you now come in and you see that here we still have the same multi-head attention. The only difference is that here it is a masked multi-head attention. So we apply that masking that we talked about where we use touch or trio. Because the reason why we are masking it is we do not want to train the model on the future versions of the sequence. We want it to predict. So we have to mask the future, right? Because here you are giving this output. This output is supposed to be what, again, the label data, what it's supposed to predict. But you don't want to show it the future. You only want to show it what it has already predicted. So you will mask the future. And that's done again, if you remember, it is always going to be a matrix like this. And the future is always towards the right, okay? And then when we're writing it, the future is also towards down. So everything to the right and down on this side, we'll set it to 0. We don't want this to be part of the training data to the transformer, okay? So we'll mask it. And it's only this side that will allow, which is what has already passed, what it has already predicted. So we pass that. That's the masked multi-head attention. It's basically the same thing as the regular multi-head attention. The only difference is that we now have a masking layer after the QK, right? After the QK, which is the attention matrix, you will mask it before you pass it into the okay, you scale it. Well, you can mask it before scaling, or you can scale it before masking. It doesn't really matter. The scaling is just a single um scalar value that you divide. So however you want to implement it, right? But you must scale, you must mask before you soft max. Then you soft max it. And when you soft max, you are now going to get this output, right? So the output from softmax, you will now use this and pass it through a projection. This is the K projection. This one is the Q and the V projection. So we will talk about that. So you see that we have a second attention layer here, a multi-head attention layer. In this case, there is no masking because you've already masked this one here. So you now attend, but you see that in this second attention layer, we are now attending the decoder's key, right, with the encoder's um, query and value, right? The query and value will have a projection matrix, which is a learn parameter inside the decoder that will learn, right, to project into Q and V, right? And then K, it learns here. So these three still go into another attention, multi-head attention layer. And then the outcome from that, you still have add and norm. By the way, the norm, the add, what you're adding is again from the previous layer of the decoder, right? And then this now passes through a feed-forward layer, just like this one, same thing. And then you now have a linear layer. This last linear layer is now what will take this output and turn it into what you want to predict. And then you have a softmax because you want to have output probabilities. That is the architecture of the attention of the transformer, right? We're going to break this down in the next slides. So, okay. So let's look at the encoder block. Again, like I said, you have inputs, you have the self-attention, you have add and norm. So the add is a skip connection here, right? And then you have the layer normalization. And then you now pass this through a feed forward, right? Which is basically two linear layers that are stacked. Okay, and but there's a specific characteristic of those two linear layers which are very important in a feed forward layer. And then again, you have a skip connection that is brought back in here, and you have add and this. So this is how the self-attention looks like, which I've already explained. You have the input, which is the X. You have the three dense weights, which is the WQ, WK, WV, that create the projection. You now have the QKV that comes out from this. The QK goes into the math mode, which is the Q dot K transpose, right? You have the scale, which is the divided by square root of DK. You have the soft max. So you can see in the encoder block, there's no masking. You now have the soft max, right? And then that soft max output is matmuled again, which is the all of that dot V. That gives you the output from this attention. So this whole thing here is what makes up the attention block. This whole thing, that's what is the attention block. We'll talk about feed forward shortly. So those are the main things. So one of the key things, the key elements of the attention, the transformer encoder block is one, the multi-head attention, which we have already looked at. This self-attention is basically multi-head self-attention, right? We can be single-head, multi-head, or whatever, right? Then the feed-forward network, which is this one, and we're going to talk about it shortly. The residual connections, which are the skip connections. So these are the residual connections, this and this, right? These are the skip, right? And sometimes we call them residual, but sometimes we call them skip, right? So those are the two. Then the layer norms, right? So this norm you are seeing here, that's a layer norm. So you have two layer norms. After each output, you have a layer norm. The essence of layer norm is that you want to normalize the values. So remember, we always talk about why are we doing standardization? Why are we doing normalization? The reason is because you want the values to go back into a certain range so that your neural network models can train faster and they will not blow up due to exploding gradients or vanishing gradients. That's the essence of norm. So in this case, we have a layer norm where the normalization is across the layer, not across the batch, across the layer for all batches, right, in that layer. So that's what layer norm does. The same thing that we were doing with standardization or normalization is just to bring the values back into something that we can manage. So why do we have the residual connections? I think I've explained it before. It's also to prevent vanishing gradients, the same way that it was done for LSTMs, right? Because by preventing the vanishing gradients, um, it prevents it by allowing a piece of the input to come back in and kind of counter the gradients inside this self-attention or feed forward, right? So it allows very deep models. So think of it like when we're doing LSTMs, there's a little additive bit to it, right? That additive bit is the X. So after you have applied X into the layer itself, this is applying X through the layer, that's layer X. You still sum it with the X. So the thing becomes more of a summation rather than a product. Same principle with the LSTMs. So it enables very deep models because then you can have so many deep models without having exploding gradients because of the summation influence of the skip connections, which is what we call residual connections. It's called residual as well because it is kind of a residual from the previous layer that comes into to influence the output from the current layer. So one other thing that enables transformers to have lots of layer is that scaling, that square root of decay, right? They call it deep norm. There's actually a terminology for it. It's called deep norm. It actually really helps with being able to minimize exploding gradients and all of that. So that's the encoder. Now we move on to the decoder. Decoder is basically the same as the encoder. The only difference is that, like you said, you start off with a masked self-attention, right? So the masked self-attention, the only main difference is that you now have this masking layer. So after you do the input, you have the projection, the WQ, WK, WV that gives you the QKV projections. The Q and K, you does the math mode, which is Q dot K transpose, right? You scale it, divide by square root of DK, which is the depth of each head, right? That now gives you the output. You now mask it. So in the first layer of the decoder block, rather, you will mask the self-attention because you don't want to train this model on future um, parts of the sequence. So you mask it. And then you do the softmax just like others. And then you take that softmax, you multiply it by the dense, a math mole, a dot product. So that will be A dot V, and that gives you this output. This is the output that we are now getting from the first layer. So this gives us the first layer of this, right? And then this output, you can see it, we have add and norm. So you have the skip connection or the residual connection just like before. And its purpose again is to eliminate vanishing gradients by converting that, product into more of a sum, right? So you have add and normalization. Now, the interesting thing is that for the decoder, we introduce a second layer, a second attention layer. But in this second attention layer, we call it a cross attention layer. It is no more a self attention layer. It's a cross attention layer. And why is cross attention is because you are now going to take K and V, key and value, from the encoder, right? And then you take the query from the decoder, right? So the decoder, okay, so I think I mixed it up in the previous slide. The decoder is going to query and say, okay, here is what, remember when I started, there's a slide I said the Q is, this is what do I want to predict next? That is what comes from here. So that's a query. What do I want to predict next? So that comes from the decoder's previous layer. And the interesting thing is that you will have a projection here, which I didn't mention. So you're still going to have a projection for this one as well, right? This is basically the same thing. It's still the same thing. The only difference is that this input, you are now getting the Q and the K rather and the V are coming from the encoder, right? The K and the V are coming from the encoder, rather from the decoder. And then this Q is coming from the decoder. There will still be a projection matrix, a weights matrix here, WQ, WK, WV, that will now project onto the QKV that comes into this second cross attention. But the main thing is that your K and V are now coming from the encoder output, right? You have the projection matrices here. And then the Q is going to come from the previous masked self-attention layer and pass through this. The same thing will happen. The only difference is that in this second layer, there is no masking because you've already masked in the previous layer. So you are just going to have a matmul, a scale, and then the scale will go straight into the softmax. And then you go into another matmul where you matmul the attention, the cross attention, the cross attention A dot V, which is the V that comes from here. So what this means is that you use the Q from the decoder to decide which values from the encoder matter. That's a QK matrix, matmul, matrix multiplication. Then you scale it, divide by square of dk, which is the depth of each of the heads. Then you softmax it, right? And you have the A. That's the A, meaning the attention matrix. And it's always going to be sequence length times sequence length, 1024 by 1024, whatever your sequence length is. Then you now say, okay, what are these values? What are the values that come from the encoder? You now use that, and that gives you your output. That's the output from the cross attention. So you have a self attention layer, and then you have a second layer, the cross attention layer. You are still going to have the residual skip connection here, right? And you add it, and then you do a layer normalization to bring the values back into an acceptable range, right? And then you pass it through the feed forward as we did with the encoder. And the feed forward is two stacks of dense layers, which I'll talk about in the next slide. And from this feed forward, the output from it, we're still going to do another, skip connection again to maintain, the gradients to be stable and avoid vanishing gradients. And then this output is finally the output from the decoder layer. So if we go back to this, remember, the output from the decoder layer, right, we now pass it into a linear layer here. So that is what we will now pass. The output from this decoder layer will pass into a linear layer, pass into softmax, and that's what we use for our prediction. So that is the decoder layer. Now, let's talk about the last component of this, which is the feed-forward network. So what's a feed-forward network? Okay, before I go into that, so let me just summarize this. Decoder has one extra attention layer. So in addition to the masked self-attention, in summary, with the addition and layer norm, we now have a cross attention, which goes to the cross attention is from the encoder output, basically attending to the encoder output to get a key and value, projections, basically. And then we put that into the feed forward. So the essence of the cross attention, the queries will come from the decoder, while the keys and values come from the encoder. This allows the decoder to ask which input tokens are relevant right now. And the decoder is able to ask that because it has its own projection of the query. That's why it's called query. It's basically to say, tell me which tokens matter, right? And then when I figure out the tokens that matter, which I do by doing the dot production to dot product with the keys, okay, I then use that to figure out the actual values. So that is summary of the decoder block. Now we mentioned feed forward in both cases. The feed forward is basically a small multi-layer perceptron, basically a two layers, right? Dense layers, fully connected layers. That's why it's called a feed-forward network, because it's just feed-forward. And what it does basically is, yeah, you take basically that's what it is. Forget about this mathematical formula. It's basically saying you take weight one, you multiply by X, which is the input plus the bias. So this first part, right, is the formula for this is the formula for the weighted sum, right? And between the two layers, there is no activation. So this is one thing to note. There is no activation. Basically, it is two dense layers, okay? The first dense layer and the second dense layer. So the first dense layer has weight one, and the second dense layer has weight two, right? And you take the X and you multiply it. So what's coming out from here is X dot weight one. Then if you have a bias, you now add the plus bias one. And that's what we have here, right? Okay, so sorry, let me back up there. It is ReLU. That's what the max zero comma this means. Basically, you have a ReLU activation here. So there are other activations that can be passed in. So this is a ReLU activation. This now goes into W2, and so you will now still have a B2, right? And you can call this um let's call it A1, which is activation that comes from the first one. So you also have this, right? And it's going to also be A1, right? Dot W2 plus B2. So this is straightforward linear layer, right? Two linear layers. But the most interesting thing about the feed-forward network is that the number of neurons in this layer is always, the number of neurons in this layer is always twice the number of, well, not always, but typically, right? The number of neurons in the second hidden layer is always twice the number of neurons in the first hidden layer. So here you have input of 512, right? And oh, sorry, let me back that up. Let me correct myself. The inputs, so you have an input of n, you have number of inputs n. The number of neurons in the first layer is always twice the number of inputs, right? That means the input into the second one will also be 2 times n, but the number of neurons in the second layer will go back to n, right? So the idea is to imp this is kind of it allows representational richness. Essentially, what you are doing is you are creating a new feature engineering here with twice the number of features, right? Twice the number of features. So here you have an input of 512. This dense layer gives you an output of 2048 size, basically, right? So remember, this 512 is the depth of the embedding. We now increase, this should actually be 1024, right? But then sometimes you can actually see feed-forward networks that are even more than 2 times. I just like 2 times is considered okay. Sometimes 4 times, right? Sometimes even more, right? So in this case, I think it is 4 times, right? 2048. So, but the main thing is that the number of outputs from the first hidden layer is always a multiple of the number of inputs, and it could be 2 times, 3 times, 4 times, you know, different numbers are tried. Okay. And then, but it is squeezed back to this number of inputs in the second layer, right? It is squeezed back so that this will go back to being the embedding size. And the reason for this is so that we can continue stacking the layers without having to worry about changes in the dimension. So this is a feed-forward network. Why do we need to do this? It is to introduce this representational richness. You have a whole new bunch of features that are introduced. The weights learn these new features, and these weights also learn how to recombine these new features to form another set. So there's a bit of re-engineering, a bit of feature re-engineering essentially that happens in the feed-forward network. And so it also helps, mixing of tokens, right? So the thing is this: if you look at in terms of the activities or the responsibilities, the attention layer, right, mixes up the tokens, but the feed-forward network now deepens the understanding of that token by creating new features and remixing those new features. So the interesting thing is that a feed-forward network contains a large fraction of the parameters, mainly because of this duplication of the number of um, um, you know, um, the number of neurons in that layer. So if you look at it, right, if you wanted to do this, since it's a dense layer, this one is going to have 5112 times 2048, parameters. And this one is also going to have 2048, times 5112. So if effectively it's going to be 2 times 5112 times 2048. That's the total number of parameters that you will have, you know, in this feed-forward network, right? So that's a feed-forward network. Then the last piece I want to just talk about um, is layer normalization. So what's okay, I've talked about that already. Positional encoding. So positional encoding is very important. Like we said, um, the the transformer does not have any inkling or any knowledge of sequence or order, right? So we have to create a, a an artificial, right, understanding of order, right? So we use positional encoding. Um, Attention is permutation invariant. That's what that means. Permutation, it means the order of things matters. Permutation is when you change order of things, right? So if you were to do the dog chase the cat, right, the attention model would interpret it to mean the same thing as the cat chased the dog, because the sequence of the words doesn't really matter. In fact, they chase dog the day, right? They chase dog cats day it will still interpret all of those to mean the same thing. Whatever permutation of these words, it will not make any sense, because when you reorder things, the transformer will not be able to know the difference. So how do we solve this problem? We use what we call position signal. So the original transformer paper used what we call a sinusoidal encoding. So for those of us who did a little bit of maths and physics, a sinusoid is basically a sine wave or a cosine wave, right? Depending on where zero starts. Now, so what they used to do was, for each position, so think about this way. This is a sequence. The dog chased the cat. So what they will do is that they will take the value at each position and use it to modulate the position, right? They will take the value at each position and use it to modulate. So this is just me using an example. So what this means is that the value, it can either be concatenation or addition, but typically they do concatenation. So let's look at it this way. In this one, we have the vector encoding of this. Let's say THE is 0.5, right? 0.8, right? 0.1 minus 0.2, right? This is just 1, 2, 3, 4, right? So what I'll do is I'll look at the position, the value of it's in position 0. The value of the sinusoid, the sine wave is 0. So I'll concat it at the end. That will now be 0.0. So in this way, I have encoded the position into the embedding as well. I've encoded the position. So this first part is the actual embedding, right? While this second part is the encoding, the position encoding. So for this one that is dog, let's say dog has another set of vectors, 0.5, 0.1, minus 0.6, minus 0.8. So this 4 forms the embedding for dog. But the position here, let's assume this position was 0.9, for example. So I'll now add 0.9 here and concat it to this vector, right? So that encodes the position. Same thing with chase. So maybe this is, I don't know, maybe 0.8, I have embedding for chase, maybe 0.2, 0.1 minus 0.8 minus 0.7, right? That's the embedding for chase. Then the position encoding is now 0.8. So this one, THE, remember THE will have the same embedding as this THE. So it will still be the same thing, right? 0.5. This is not yet, we do position encoding before it goes into attention. So there is no difference in the embedding. The embedding is directly semantic and is directly, the same based on the word. So in this case, the word THE is the same as this THE. Forget about the case, right? 0.5, 0.8. 0.1, right? Minus 0.2. So this is the same embedding. But in this case now, the position is minus maybe 0.6. So you can now see that this is how I now, even though this is the same THE and THE, but I am now able to improve or encode the position of the word using this. So you can now say that the resultant vector here is not the same as the resultant vector here. And this extra one is kind of indicating the position. And the same thing will just go on like that. So that's what position encoding does. And this is using a cosine. There are many other ways. You could even just use linear, for example, right? Where you could say for each position, you have a corresponding mapping. So there are many ways of positional encoding, which I think we will look at. So positional encoding is how we can now introduce additional encoding for the position of the word or the token in the sequence, right? So like I said, the original transformer paper, they use sinusoidal. So this is typically the formula. Positional encoding POS, comma 2i is sine of POS over 1000. Typically, they do a bit of, scaling of the values to avoid vanishing gradients and all of those. So it's basically a position. This position POS means the position of the token in the sequence, starting from 0 to whatever the sequence length is. And you use that. So this is typically like 10,000, maybe to scale it so that it doesn't go above 1. So if you are looking at sequence length of maybe 10,000, right? Then it means a 10,000 um, 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 word or token in that sequence will have 10,000 over 10,000, right? Which will be 1, right? But you also are going to take that and do 2i over d, which is this what brings about the sinusoidal nature. The reason for sinusoidal is so it does not become too high. You also end up with gradients and so on. So these are the formulas that they use for cosine, for sine position encoding and cosine position encoding. Now, the question you may ask is, how did they even come about this sine cosine? It was really basically based on looking for what would be the best pattern that will really make sense. So, position encoding is one of the things that researchers still try different formulas to figure out, okay, which one would be the best and so on. So, why sine or cos at the end of the day? Because sine and cos can give you unique patterns and you can have infinite extrapolation. What that means is that because it is sinusoidal, even if the value of the position is infinite, it will never be above 1 and it will never be below -1, right? It will always be within that range. So you do not have the concern or fear of exploding gradients, right? Or vanishing gradients for, well, it will not have a minus infinity because its position is always going to be a positive integer. But the idea is that sine and cosine ensures that no matter how far away, right, you will never get the thing blowing up. And then it encodes relative distance. Okay. So this is the PyTorch implementation. It's a very simple thing. Torch does zeros for position in range sequence length. So you go from 0 to the maximum length, which is the sequence length. And so for each of that, D model, by the way, D model is the depth of the model. In other words, the depth, the embedding depth, which is 512 for the example we have been using today, right? You can use a different thing. That's what D model is, please, in case you see this. Then, so what you are saying is that for I in the range of 0 to D model, so you are looking at embedding depth from 0, okay, to embedding depth, step of 2, right? You now do this. So basically using this formula, essentially, this is just this formula they're using here. Position, the angle is position divided by 10,000 raised to power I over D model, which is, because this is 2I over D. But since we are using steps of 2, it gives us basically the same thing. So the positioning encoding of position I will be math.sine of the angle, and the position encoding of position I plus 1 is math dot cos. So what they are doing basically is that position 0, we use the sine formula. Position 1, you use the cosine formula. Position 2, you go back to using the sine formula. Position 3, you go back to using cosine formula, and you keep alternating like that. That is the approach that they use. So for 2I, where I is any integer, use sine. For 2I plus 1, which is the odd number position, you use the cosine equation. And that's basically this, right? You probably don't need to do this yourself, but we can try it out. So we've talked about that. So it's a very nice thing from mathematics, right? We can simply add it, okay? So token embeddings plus PE, right? This plus doesn't actually mean sum, please. It actually means concatenation. It basically means concatenation. And um, yeah, it's concatenation. I'm trying to remember if anybody has used addition as yeah, but addition would just change the value of the embeddings, which is not what we want. It will morph the embeddings. But concatenation um adds additional encoding to the embedding. So that's a positional encoding. So at the end of the day, right, the interesting thing is that when you are building a transformer, you're not really going to do a lot of that stuff, right? You're basically just going to call this function transformer encoder layer. Okay. You specify the D model, specify the number of heads, like we've said. You choose the number of heads, and then the dimension of the feed forward. So this dimension of feed forward, remember I said the feed forward network, you always have this is times something. So in this case, for a 2048, right, we specify the dimension of feed forward to be 2048, right? So basically, we are saying 512 will go into the first feed forward layer, and what will come out, the number of neurons in the output in that first layer will be 2048. And then 2048 will go into the second layer, and the number that will come out will be 512 again. That's always the architecture, right? What goes in is what comes out, but what is in between is what you specify here. And with this, you have specified a single layer. So essentially, what we are saying is I have defined what a single transformer encoder layer looks like, okay? Then I can now create an encoder by stacking a certain number of encoder layers. And we are stacking 6 layers, right? 6 of these particular encoder layers. And that's it, right? And you pass your touch, you create your X, basically, touch random 32, batch size of 32. 50 is the sequence length, and 5, so that's a sequence of 50 words or tokens. And then 512 is the embedding depth of each token, right? And you run that, and that's it. So this is basically, um, you know, how transformers work. So a few other things I just want to touch on. There are other improvements in recent times that have been added to the transformer architecture. So you have what we call the rope. So rope is another kind of positional embedding, right? It's called rotary positional embedding. So rather than using the sinusoidal, right, they use this positional embedding. Um, so what this does is that it helps to basically increase the context length and help transformers to handle longer context length, right? You can see it's used in a lot of the GPTs, GPT, Neo X, Llama, Mistral, right? The whole idea is to rotate the vectors in embedding space. Okay, so that's what group does. Unlike just doing a sinusoidal thing, right? So what this does is includes the relative position more naturally, okay, of the embeddings. It's better because it has a strong long context performance. There's smooth extrapolation and there's a better attention decay. So rope is one of the reasons why modern um, LLMs and models can handle 100,000 plus tokens, right? The other thing that they did is what we call multi-query and group query attention. So typically, multi-attention, this is kind of a summary of what I explained. You can see here you have a scale dot product attention. You have multiple of it in parallel. This is the multi-head. H is the number of heads. And you have each of them has a separate linear projection, right? And then each of them has a separate output of V. Those are now concatenated like I showed you, and then passed through a linear model. This is a very expensive memory wise, because first of all, an attention is taking 1024 by 1024 if you're using a single attention, right? Even if you're using a multi-head attention, you see 1024 by 1024. But it's even worse if you are using a multi-head because you now have that times the number of heads, right? And then each of the matrices also are big because you have the depth of the embedding, 5112, times the sequence length, which is whatever it is, right? So it's very memory expensive. For a sequence length of 1024, that's cool, right? But now think about large language models of today that may have context lengths of sequence lengths of 100,000 tokens. So it becomes really large, really memory consuming, memory expensive, right? And each head is storing separate K and V matrices. So they came up with this. Some of the ways they came up to solve it was a multi-query attention where the many heads will share one key and one value, right? But it's only the query that will be different, okay? Um, the result is that you have faster inference, lower memory, and it's ideal for production large language models. And you can see it's used in Palm and Falcon, right? Then you also have another one called a group query attention, right? This is now a bit a middle ground between the multi-query attention and the original multi-head attention, where you now have multiple heads, switching between multi-queries, right? So what that does is that it helps to balance quality and speed. And it's used in Llama 2 and Mistral. So there are a bunch of improvements and so on. Then we have what we call a flash attention. Flash attention still uses the same multi-head attention mechanism, but they try to improve on their algorithm because the attention complexity, apart from consuming memory because of that, it also consumes compute. It takes time to calculate simply because it is O(n) squared, right? Where n is the sequence size, right? You're basically squaring the sequence length or the context length to be able to achieve the attention mapping, right? So again, memory is a bottleneck. So the idea with flash attention is that you now compute the attention in GPU static RAM blocks. Basically, you now have um, hardware customized to handle attention, right? That's basically, we now move these matrices from having them in DRAM, which is a dynamic RAM in the computers, into SRAM, which is static RAM, which are um, basically they can handle it and they can handle it in parallel, right? You can just keep them there in the GPU, right? So that kind of helps to speed up the calculation. So some of the benefits you see is 2 to 4 times speed up, right? You now have a massive reduction in the memory demand, and you can also have longer context training. Of course, if you have massive reduction in memory, it means you can have more context because memory is always the bottleneck. So it's more of an algorithmic optimization. The architecture is still the same. It's just that we are now pushing into GPS RAM, and a lot of frameworks are already using it. Then there is a new research that is going on in what we call linear attention. So instead of using the square the attention matrix of sequence length times sequence length, right? where everything is a complexity n squared, basically the compute complexity. We now have linear, so the the complexity is n, which will be a much faster computation, right? So the whole idea is that one of it is approximate softmax using kernel tricks, because softmax actually is part of the things that is the O n squared, right? So but at the end of the day, you end up having very long sequences, and sometimes you have low accuracy. That's still in research. There are a few uh, kind of proof of concepts and examples, but we've not really had them used in practice. So this is the transformer architecture, and some of the key takeaways from this is attention will allow your models to focus dynamically. Self-attention enables the parallelization, right? Transformers allowed us to remove LSTMs and GRUs and all recurrent neural networks from the whole system, from the whole architecture, enabling much faster training, much more parallelized training. Then positional encoding, because the attention mechanism itself and the transformer architecture itself using linear layers, right, does not, the linear projection of the QKV as well as the position encoding, well, position encoding is a solution because the QKV linear projections don't know anything about sequence, right? So you have to introduce sequence, and the way you do that is using position encoding. And then, of course, the multi-head attention allows you to learn diverse relationships. So that is a summary of our attention um, and transformer architecture. Are there any questions? I would like us to just do a quick hands-on um, on just build a very simple network, right? Using the transformer architecture, right? A very simple network. I am going to speed this up very fast. I had actually already started, so I'm just going to um, pull that in. So I want us to do, if you remember, we had done prediction of the next word, right? For a very simple scenario where we had 3 or 4 sentences. Now I want to do prediction of the next word using the IMDb, which is the database. I started it last time, but the training with LSTM, I didn't even finish. I had to abort it, right? So this is next word prediction from IMDb dataset, right? Using transformer. So we just use a basic transformer architecture. So first of all, of course, we do the imports, we load the IMDb um, data set, which we can, the IMDb data set actually comes with PyTorch. So we can load it from the PyTorch data sets, right? Library. So we'll have to install this library. We don't have it already. You just call on load dataset and you specify which dataset. The IMDb already is kind of registered there. So you pull it in. And then this dataset has a bunch of text, but we'll start with train text, right? There's also test text, which we use for the test. Right. Now we are this IMDb has close to or above 50, 60,000 um different sentences, right? Different, sentences. The vocabulary can even be larger than that. So this, we are just taking a small fraction because I want to be able to finish this. I want to be able to finish training demo quickly, but we can train on the whole bunch. So I've run this. You can see it has downloaded this already. We implement a simple tokenizer, so you can already see we have a tokenizer setup. This is a very simple tokenizer. It just splits on word boundaries, basically on spaces, nothing more complex than that. Then we now create our vocabulary. So going by what we did last time, we create our vocabulary. Our vocabulary, we use a counter, right? And we now tokenize the words in the text, right? We've taken the text out from here. So remember, we took the text from train text, right? So for each of the text, we can actually check out what is in train text, right? So we just check there's stuff in it. There's a lot of stuff in it. I probably don't want to print out the whole thing, but let's just print out maybe the first few sentences. So let's just say the first 10 sentences. Um, this has about 10,000. So the first 10 sentences, so you can see them here. So I think I would let me join, right? Let me join. Let me join. So let me join with a new line so that we can see. Yeah, I want. Yeah, so I don't know if the new lines are coming through. Okay, they're coming through. So let's see if they'll come through in Markdown. Well, it didn't really come through in Markdown. Let me see if I use double, whether it will come through. Okay, let me use Markdown and see how I can maybe use a Markdown thing like this to see. Okay, so I still need to import the Markdown. So let me import from IPython dot display import Markdown. Yeah, okay. I'm forcing it to use Markdown. Yeah, okay. So forcing it to use Markdown. This is a yeah. Let me use double slash. So these are just 10 sentences, but you can see that these sentences can also be quite long. These are 10 sentences, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are really long sentences with a lot of vocabulary in them. And I can see why it took so long to train an LSTM on it. Okay, so now I build a vocabulary. So we tokenize each of the text, each of the words in that, right? We tokenize them and we get the tokens. We add it into our counter. So our counter is effectively building the vocabulary. And we now kind of we will not use every single word in the vocabulary. We'll rather just take the 20,000 most common words. So what we are doing essentially is we use a counter to pull the most common based on vocabulary size -2. So the essence of -2 is we want to reserve two spaces, one for the pad and the other one for the unknown like we did last time. So that's what we do. So we get the most common words. We do string to int, which is basically um, the dictionary that will allow us to map strings into the correct integer index like we did the last time. And we run this to complete it. So we've done for 0 and 1, which is 0 is pad, unknown is 1. And then we just run enumerate. We start from 2. We start from the second position in the most common one. And we basically just, for each word, we do that. Start to string to index. So then we index to string, we just reverse it. So use a reverse lookup table and we generate that. So that gives us our two lookup tables. So we now do encoding. So to do encoding, we encoding is going to basically be tokenize, right? After you tokenize, then we will now just find the index, right? So we check the token And from the string to index, right, we take the value of the token, right? The value of the token from the string to index. If we don't find it, then we use the unknown, which in this case is going to be zero anyway. It's one rather. So this does the encoding. Okay. So that's what I did so far. Now, so let's continue. Um, we now need to create the embedding matrix, right? Because after you have done the encoding, right, you need to create the language data set, right? The language data set is going to contain the vocabulary, right? And um, well, the entire data that we are trying to load. So we'll create the language data set. So to do that, so this is a code for it. So you can see that what we are doing here is yeah, so we this is the constructor, right? So the initialization function, you specify the sequence length, which is the maximum sequence that you want to train your model on. You put that in as a parameter. Then this data contains all the data in the data set. So we will then you pass in all the texts that you want. So in this case, this will be the whole thing in IMDb, which is the this whole list of sentences in IMDb, which we printed out a few of them. Let me see. I think we printed out a few of them here. So yeah, we'll now take that. So the process, what's going on here basically is encode each word, and then for each word, right, we will also do um this, right? So basically for I in range, length of encoded minus sequence length, right? So the thing is this, remember the encode is going to give you the position, the index, right? Which is what you pass into your embedding this thing. So this is what we did before, right? Um, we're now going to get the X values. So the X value, um, so let me explain this. I think the best way is the way we did it before, where we said, okay, you are training the language model. So we need to create the language model data set. And this is the language model data set. Basically, what you are saying is that for each word, for each sentence, okay, for example, this, right? You need to generate the prediction, right? Now, unlike when we were doing a next word prediction, we are going to predict. So this is the right shift we are talking about, right? We are going to do right shift. So this is the input word, the movie was, right? Now, because the sequence length is kind of fixed, right? What we are saying is the movie was, then we right shift it. So movie was great. So this is what the encoder is going to see. And this is what the decoder is you are going to use to train the decoder. So this is basically what that is. So I just wanted to um, tell you what this is doing. So you can see how it does that is that for each text, right, that has been pulled in and encoded, you will find the balance, the remaining words. Basically, you have the length of encoded, which is the length of the that word, the words, right? The this the rest of the spaces, right? You need to fill it with stuff. So you take the X would be the value from the current I, to the sequence length, and then the Y will be from the next one to the sequence length from one. And then you append that, right? You append X and Y. So essentially what you're saying is um, the X value is this, right? You are generating the data set that you are training. The X value will be this, Y, right? While the Y value is the from the next word to um the to the end. So that's really what this does. And um for each of the encoded word, it will give you that. Yeah. So this is basically a data set that will transform the IMDb set like this, like a single sentence, for example, this, into a sequence that is made up of this. Um, to look at what comes out, the outcome of this, right? Get item is just to get each item. When you get the item, you now convert it to a touch tensor, basically, right? Um, Again, remember that we are essentially generating indices. So what you're doing is you're not generating the actual words, but the indexes or indices that correspond to the words, right? And yeah, so that's it. The next one, sequence length plus one. You convert those into a touch tensor. So if we create a new data set, which is the next thing to do, right? We can then look at it. So we create a new data set from this class. We pass in the train text, which is the um, basically the what we have loaded from the IMDb, right? And you can see we loaded um, the first 10,000, right? So all of that is what we'll use to create a data set, and then we'll create a data loader, right? Remember, a data loader is just a way to load data from data set in batches. Since the data set may be too large for you to fit everything into memory, you definitely need to load in batches and train in batches. So we create a data loader. And when you create a data loader, you can actually view the elements in a data loader up to this batch size. So if, for example, I say next loader, it's going to show me what is in. Yeah, it's taking a while to build this because of the large amount of um, words, right, in the IMDb data set. So yeah, so loader dot um, I don't know if I just say loader dot zero, and we'll see what we get. Okay, so it's not easy to access that way. Um, okay, so you iterate it's not subscriptable. Okay, let's proceed. We can look at that later on. So remember we said that for a transformer model, after you have loaded the data, that's the X data. So if you remember this, let's see, let me just look for a nice image of the transformer so that we will be able to it's a good idea to go and study a little bit on the transformer architecture. So this is it, right? So remember, when you get your sequence, your source sequence coming in, you do embeddings first, right? So you do the embedding and projections. In this projection, it's not a QKV projection, but rather it is just your embeddings. So after embedding, you need to do position encoding. So we have just done a data set, right? We'll need to do a position encoder. So let's look at the position encoder. Um, we'll pull all of these parts together later on. Now, the position encoder Um, so this is the position encoder. And remember, we had already looked at the mathematics around the position encoder, so I can check it out again, right? Um, but this is it, right? You basically will go through the sequence length and generate position encoding, and then you just return that. So the position encoding depends on the sequence length, which in this case, if we use 50, but it could be larger, and the D model, which is the depth of the model, basically the embedding depth. Okay, so it's essentially the same thing. Um, so in this case, we start with touch dot zeros, right? It's basically the same thing here that we are doing here, except that it's a vectorized approach. Position is touch dot a range, which gets a range from 0 to max length, right? We specify the max length of the position encoding. On squeeze one basically means make it into a flat um, a two-dimensional um, on squeeze from dimension one. So on squeeze means basically make it two-dimensional. So um, yeah, okay. So you have two-dimensional. Then touch dot exponent, touch dot a range. So if you remember the equation we did here, there is um 10,000 raised to power 2i over d. That's the exponent, right? So so this touch dot exponent, touch dot a range 0 model. So this is again, touch dot a range gives us a range of numbers that start from 0 to d model, right? Skipping twos. And then you multiply that by minus math log 1000 over d model. So this is div term, the division term, right? So that's just to generate this division, um, this this part of it, this 1000 raised to power 2 I over d. That's what that does. So um, that this is the 1000 divided by d model. D model is the depth, right? Which is d, is the depth, embedding depth, which is d. So all of this basically does all that. I'm not going to analyze it too much. So when you get that, you now multiply that by the position and you take the sign of it for all the e- um these are all the even number parts from 0 to the end, skipping two, skipping every every even number basically. While this is every odd number, starting from one and skipping every two positions. So for every odd number, you do cosine. For every even number, you do sine. So this is like the original implementation. So this was doing it in a loop, right? But this is doing using touch and vectorization. And then after that, we unsqueeze and basically spread it out. So that's positional encoding. Now, um, because we are going to do this as a layer. So this is implemented as a layer. You can see we are subclassing the NN dot module. So this is a layer, and that's why we have to use this vectorized approach rather than the more easy to understand, the easier to understand looping. But you cannot use looping in this, it will be terrible, it will be very slow. So that's defining the actions. And so to now run the forward, on it, you will X plus. So this is first of all generating the numbers that you will add, right? And then you just do X plus. So here we're actually just doing X plus, right? X, which is the thing, and self.pe, which is this, right? And then from this to whatever the size of X is. So essentially, you are generating a list of positional positions, and then you move it into whatever device that X is on, and then you do the math. So this is simple implementation of a positional encoding layer, right? Um, so after position encoding, right, the next thing you do is the multi-head attention, right? This is just a multi-head attention. Now, this is what we call a pre norm, right? Not a post norm. I need to check what we are doing. What I was teaching before was a pre norm. The normalization is before the multi-head attention. What I was teaching was a post layer norm, right? A post layer norm, which is what we have here, right? A post layer norm. But the layer norm comes after the attention. But I went and picked, I wasn't paying much attention when I picked this image, right? But this is a pre-layer norm where the layer norm is happening before the multi-head attention. But you still have this skip connection, the residual connection. So anyway, what we are going to implement will be a pre-layer norm. But anyway, so this is now the entire transformer model encoder first. So let's look at this, right? So you have the entire transformer layer, right? Um, Single layer, right, of a transformer. So you have the input embedding. So remember, we have an embedding model, and we're going to pass in the vocabulary size and the D model. The D model again is the depth of the embedding depth, right? Basically the depth of the model. Vocabulary size. So we did this already. Use the embedding model, specify vocabulary size. The vocabulary size is obviously the size of our STOI, right? That's the vocabulary size. Even though it's sometimes it's said that you should, yeah, you put the whole STOI, but you need to specify the zero padding, the padding index. Then the position encoding. So we also have a position encoding layer which we create here, and we pass in the D model, which is the size, the depth of the model. So remember the forward of the position encoding layer is going to take X, whatever it is, and concatenate it or add it. Um, yeah, I need to check this, right? So I think it is a sum this time around. It's not a concatenation. It's a sum. So let's pay attention. It is actually a sum. That's why we have its plus here. So I've also seen position encoding done with concatenation, but this is a plus. This is a plus. So it's a sum. So you're actually adding the I know that when I was teaching, I did a concatenation where you appended the the equivalent tensor, right, for the position encoding. But here it is being added. So we're essentially generating a tensor that has the same, has a maximum, a very long length, a maximum length of 5,000. And then we are taking the subset of that tensor, right, that matches the length of the input X. And we're actually doing a sum, a plus sum with the X input. So that's position encoding. So after position encoding, a decoder layer is created. So this is a standard transformer decoder layer, right? We specify the depth of the model, which is the encoding. We specify the number of heads. This is passed in as parameters. Default number of heads is 4. Default D model is 256. Maybe we want to make it match what we did. It's 5, 1, 12, and 8. But this might be a bit too much to train. So let me go back to the 256, which is the depth of the embedding depth, and the four heads. Then batch first is true. So we create a decoder layer, then we create a stack of decoder layers, right? And the stack of decoder layers we create here, we create specify the numbers here. So here specifies 4. And then we specify a linear layer. Right. So the interesting thing you will see here is that there is no encoder layer here, right? There's no encoder layer in this transform model. It's just a decoder layer. And this follows the architecture of BERT. BERT did not have, or GPT style only has decoders, right? It doesn't have encoders, which is quite interesting, right? So we need to also generate a mask. So you can see this is how we generate the mask. We use touch.tree like we saw the other time. You can also see when we were talking about masking. Where is masking? I think I may have This is scale dot product. This is mask attention. So you use tree, you get ones, you specify on the first diagonal, right? The ones have to be sequence length by sequence length. So remember that is the dimension of the attention matrix, okay? And then you do a field mask, and that's basically what we are doing here. So we take a triu of size, which is the attention size, diagonal one. You still do the mask field, right? And the mask, you check where mask equals to 1, which will be the upper side. And you fill that with the value of minus in, right? And then you return that mask. So that is what will be used to multiply with the actual value of the attention, right, before the soft marks. Okay, so the forward is you get the sequence length, right, which is the size of the first dimension. So again, remember, this is batch sequence length and embedding. So the first dimension, the 0 dimension is the batch, the first is the sequence length, and the second is the embedding size or the D model. Then we get the mask. So we get this mask, right? And we put the mask into the GPU, if it is a GPU, right? Then we, first of all, we'll run the embedding. So if you look at this, remember, we'll need to run embedding first. So embedding is going to generate our embedding vectors. So you're now going to have batch times sequence length times the embedding depth, which should be 256. I guess we should have, that should be a pass-in parameter here. That's the D model. Okay. So sorry, that's not a D. Yeah, okay, D model, the embedding depth. Yeah, so we generate that. We generate an embedding, right? And from the X, we pass the embedding through position encoding. So again, remember, after embedding, the next thing is positional encoding, which is you generate the positional encoding that has been generated and you sum it up with the embedding. And then you are going to pass it into the multi-head attention. In this case, I think it is a pre-layer norm. The beauty of using the built-in, in this case, we are just using a decoder. So we're not actually using encoder. In this case, we're just training it using the decoder. So we have, again, I guess I should give you a different drawing for that because that is just a decoder only model. In a decoder only model, there's no cross attention because there's no encoder. You can only do encoder when, sorry, you can only do cross attention when there's an encoder, but there's no encoder in this case. So embedding dimensions, you do your norm. You now do the mass multi-head self-attention, which is what we did here. Basically embedding, and then we pass this embedding to the transformer. So the transformer will basically do, where is the transformer? So the transformer is a transformer decoder, right? And the transformer decoder does this, right? Which is mask multi-head, but we need to pass a mask into it. So yeah, this allows us to pass in a target mask. So that's the beauty of the transformer decoder, the class that Python gives to us. So we are able to pass in the embedding itself and the embedding again, which I guess one of them would have been the outputs. This is if you look at this, it is going to there are two things you are passing in. The first is the uh, the decoder input, and the other one is the encoder input. So that's, but we are essentially using position encoding. We're essentially using this positioning encoding not twice. So the output is the output that comes from this entire decoder stack, right? It has all of this, so we don't need to do all of this mass multi-head and all of this and the feed forward. This entire class does all of that for us. And that's it. So the output we get here is the output that comes out from here, right? We just do a linear layer. We're not going to do a norm. We just do a linear layer, which is the fully connected layer out here, right? And that's it. So this is very simple implementation. Um, it actually doesn't much match this. It's much simpler than this drawing, but that's the implementation. Okay, so the next thing is training, right? So to train this model, um, we've already done a data set. So we first of all determine which device that we want to use. If we have um a a GPU, then we'll go to GPU using CUDA. If not, we use a CPU. We now create an instance of the model transformer LM. This is the length of the vocabulary, right? So that is gets passing. This goes with the default values here. So a D model of 256, number of heads, 4 heads in the multi-head attention, and 4 decoder layers, basically, right? So we now go ahead and create our optimizer. We use Adam with a learning rate of 0.0003. We use cross entropy loss because cross entropy loss is what you use to train a probability distribution predictor, right? And you can see we use logits here. We did not actually put anything like soft soft um, soft mask, soft um, we didn't use sigmoid, right? Or soft max, right? We didn't use sigmoid or soft max. So we're just training with logits. And we train with cross entropy loss. The cross entropy loss will automatically apply the soft max for us, so we don't need to do that. Okay, so we've established our hyperparameters and our training. So now we go ahead into training. This is standard training. We use 5 epochs for this training. We're not going to spend too much because there's a lot of data, 10,000. If we actually check the number of items, which I let's let's see. I was trying to do this before. Loader.items. So I don't know how to access the items in a loader, right? But I can look through it. So maybe for yeah. So let's just see what is in here. We can just print X, for example, and then print Y and break. Yeah. So this is just to print a single um, input. So a single X and a single Y. And you can see these are indexes, right? These are indexes that correspond to sequences of words, right? You can see that this one starts from it starts from 11060 and ends at 4, right? This one starts from 3582, which is the second word in this, and ends at 4, right? Which corresponds to this, right? But it also has this extra word at the end, 83. So that's the right shift, which I had wanted to initially I had wanted to look at. So that's the list, and that's what we are using to train this. So we move it into the GPU or CPU. We run zero grad. We run the model. We get the logics. We get the loss, right? And we have to do a bit of reshaping to match, right? We have to do reshaping to match. Okay. Then we run backwards to calculate the gradients, and we run optimizer the step to train the model, update parameters, and then we accumulate the loss because we are looping through the data set. It's best we accumulate the loss. Then after accumulating the loss, we can do this. There are just 2 epochs, so there's a lot of data here. So we can just run this now. Okay. So this will take a bit of time, right? It will even take longer if we were using an LSCM or something. Um, yeah, because we are not, it would be nice to add some kind of progress bar here. Maybe I'll add it later on. Okay. So let me add new code while that is running. So this is a function that will generate the text, right? So how does this function generate the text? You go to a val mode, right? You encode the tokens that you want to generate, right? They start text, basically what we call prompt, okay? Then we, you know, we encode it, basically tokenize it and convert it to indexes, okay? Then we convert it to tensors, right? On squeeze to flatten it out, right? And then we move it into the CPU or GPU device. Then what we now do is that for um, you know, max length is basically saying this is the maximum number of text I want to generate. Remember what I did before, where I said, okay, generate text. When you generate, okay, you can then append it to the end and loop. So what we do now is we generate the next set of text based on the train model. We generate it as the logic, right? We pull the next token. So the next token is basically pulling the last in the sequence. Okay, we maintain the batch, which is batch one, and we maintain the embedding thing, right? So we pick the one that has the highest probability, right? And that's the next token. We now take that next token, we stretch it out, right? Into a single dimension, and we append it. We basically concatenate it with the list of tokens. So this is like saying, take the tokens is indexes, right? We now find it. It has predicted the index of the next token. So we take that index that it has predicted, right? And we still append it. Okay. And when we append it, that becomes a new set of tokens which will pass back into the model. So basically, you are just looping through to predict to whatever length of sequence that you want. When you get to that point, right? That's it. We now generate the actual string words from this token, right? That's it. And then you can then join it with spaces, and that will generate words. So we can now test that with this. I don't know if my CPU will work fast enough, but let me even just interrupt it. I don't know how far it has gone, how much it has learned, but whatever be that as it may, we'll just continue. And let's try generating. It didn't train very well, right? Yeah, it didn't train very well. So we start with this movie was we're having unknown, unknown, unknown. Yeah, mainly because we've not really trained the model very well. So let's do this. Let me switch to a GPU, and then I'll rerun this code and hope that it will run faster. Right. So let's see how fast this will run. Yeah, so that brings us basically to the end of our transformer class. I'm going to share this Jupyter notebook so you can just try it out and see if you can train your model. So what I would say is, can you train your model using this IMDb data set to be able to generate text, right? That is what I would I want to see us do. And then when we meet on Friday, we will now talk about large language models. That's all from me. Thank you.